So now we're going to look at a very similar example, but this time we know that the argument of this complex number is a negative argument, so minus pi over 6. So let's think about this purely geometrically to start with. So in order to think about this geometrically, just like we do with every other locus when we do it geometrically, we need to rewrite this in the form z minus some complex number. So inside the brackets, I'm going to have to put plus 2 and minus 5i. And that's going to ensure that when I multiply out that bracket, I'm going to have minus 2 and plus 5i. So let's sketch this point 2 minus 5i, the complex number that we're subtracting from z. So let's sketch that on an Argand diagram. So we've got that complex number there, 2 minus 5i. So what we've got to do now is we're going to think about this as z minus 2 minus 5i is the vector that starts at 2 minus 5i and goes to z. And we want the argument of that vector, that is the angle that that vector makes with the positive horizontal. So let's draw in the dashed positive horizontal to have an argument of minus pi over 6. Well, we know that the negative direction for an argument is the clockwise direction. So we can draw in the locus, it's going to be a half line which moves off at an angle of pi over 6, but in the negative clockwise direction from that positive horizontal dashed line. So we can label in that angle as pi over 6. Let's just confirm to ourselves that works. So let's say that z is a complex number which is on that locus that we've just drawn, which is there. Then inside the bracket we've got z minus this point here. So that's the complex number which starts at 2 minus 5i and moves to z. So it's that vector there. Well, what we want is we want the argument of that vector to be minus pi over 6, which is correct because you can see that it makes that angle with the positive horizontal direction. Now really what we mean is z minus 2 minus 5i is actually a complex number which has this red vector as its position vector. So in this case, for that value of z minus 2 minus 5i is actually a complex number which would be there, and its position vector would be the same as that red vector which I drew in there. And you can see that the argument of this complex number with that point there is going to be minus pi over 6. Before we move on, let's just double check why is it only a half line and why can't I extend the line up here? Well, let's say we did extend the line up there and that z lived there, for example. Then z minus 5i is going to be this green vector there. Now the argument of that green vector is actually going to be 5 pi over 6 because that angle there is 5 pi over 6. So that is wrong. So we don't want to draw that portion of the line. So next let's think about the problem algebraically. So again we're going to look at two different ways of thinking about the problem algebraically. One way would be to say, well, we know that the line goes through this point with coordinate 2 minus 5, and we know that it moves off like that, and we know that that angle is pi over 6. So one way of doing this would be to say, well, let's come up with what the gradient of this line is. So let's draw in a right angle triangle, like that. And let's label this as the opposite side length and this as the adjacent side length. Then we know by trigonometry that tan of pi over 6 is going to be equal to the opposite side length divided by the adjacent side length. Well, the gradient of this line is, well, we've got to be a little bit careful here. The vertical change, because the line's going downwards, is actually going to be minus this side length here. So minus the opposite side length. Because opposite's positive because it's a length, so the change in y is going to be minus whatever that positive value is, divided by the adjacent, which is positive. So you can see that actually the gradient of this line is going to be equal to minus tan of pi over 6, because opposite divided by the adjacent is tan of pi over 6. So the gradient of this line is going to be equal to minus root 3 over 3. So we can come up with the equation of this line. The equation of this line is going to be y minus, well, we know that it goes through this point, so y minus minus 5 equals the gradient times by x minus 2. And it doesn't simplify very nicely, and it won't always look very nice, but we should probably neaten this up a little bit. And that's the equation of our line. Now, we've got to be careful again, because we know that it's only a half line. This is only valid for values of x which are to the right of 2. So we need to have in the condition here, this is only true for x greater than 2. So finally, let's look at a different way of thinking about this line algebraically. Well, let's say that z is going to have coordinates x, y in the Argand diagram. So z is x plus iy. Then we want the argument of x plus iy. I'm just replacing z with x plus iy. Minus 2 plus 5i. So minus 2 plus 5i equals minus pi over 6. So to do this algebraically, we've got this complex number inside the bracket, and it's going to help us if we can think about this in terms of real parts and imaginary parts. So the argument of the real part is x minus 2, and if we take I outside of a bracket, the imaginary part is y plus 5. Now at this point, it really is easiest if you just remember a fact that we've already learnt about arguments. If we got a complex number w, and we know that it's got a real part and an imaginary part, and its argument is theta, then we can straight away say that tan of theta is going to be equal to the imaginary part, because we can draw in this right angle triangle, that's the opposite side length, divided by the real part. And that's true no matter what theta is. It works for negative values of theta or positive values of theta. So if we apply this to that problem here, we've got this yellow complex number here, and we're going to use the fact that if we do tan of that yellow complex number's argument, so tan of minus pi over 6, that's equal to the imaginary part, which is y plus 5, divided by the real part, which is x minus 2. So we'll end up with minus root 3 over 3 equals y plus 5 over x minus 2, and we'd get the same answer that we got before. Now, I would recommend becoming confident with this final method, because this final method is nice, quick and simple, and it just uses this fact that if you do tan of the argument, you get the imaginary part divided by the real part of the complex number.